Collider physics in the Higgs boson has been recognized with one of the highest prizes from the American Physical Society, the Sakharov Prize. But I would say what sets him apart from most of his colleagues is not his intellectual prowess, but more importantly, his ability to communicate his passion and his sincere belief that science and physics, particle physics, can help reveal the deepest secrets of our universe. Without further ado, let me introduce Dr. Christopher Quigg. Thank you. Sir.
Thank you for coming tonight. It's a great pleasure to be with this audience. You know, all of us think of ourselves as explorers, and explorers need support, of course, financial support, but even more important, being able to come home from our voyages and share our discoveries with people. And we've had the pleasure over many years of doing that with this audience in the Fermilab community. So I thank you for being part of that. It makes our work unique. So, 50 years ago, this 6,800 site on which we find 6,800 acre site on which we find ourselves looked like this. There were the 400 residents of the planned community of Weston on the east side of the laboratory. Many farm families who had settled here and tilled the soil, the Illinois soil, for many years. And it's very different now. In the space of a few short years, it became an international destination for physicists, welcoming scientists from all over the world and producing results that are valued by people all over the world. It's also named, as you've just heard, for Enrico Fermi, the Italian-American physicist, who was revered by all of us. He died in 1954, so he never got to see Fermilab, nor did we benefit directly from his input. But he was someone that we called the last universal physicist. He was a master of both theoretical physics and experimental physics. And this is something he knew all the subjects of physics and was able to communicate and teach them. So he's been one of my personal heroes, and it is wonderful for me, and I think for my colleagues, to be at a laboratory that bears his name. The founders of our laboratory, Bob Wilson and others, wanted this to be a quintessentially American laboratory, but open to the world at large. And one of their first acts was to honor the legacy of what had been here before. So you see on the east side of the laboratory in Sauk Circle, a number of the original farmhouses. Several of them are gathered together here in the building that we call Aspen East, which has served as a dormitory for many years. The little houses in the village of Weston have been used as dormitories or residences for visiting scientists, originally for labs and office space in the early days. When the national instinct to get together and to do complicated, difficult, expensive things for the common good was much in evidence. So that was good. It was also a time of social upheaval. It was a time in which the nation was coming to terms with its legacy of segregation in the past. And the funding of the laboratory was threatened by the fact that the state of Illinois and the surrounding communities had not yet adopted open housing legislation. Our founders, Bob Wilson and Ned Goldwasser, his deputy, both by that exigency but also by personal conviction, wrote this statement of human rights for Fermilab. It says in part, it will be the policy of the National Accelerator Laboratory to seek the achievement of its scientific goals within a framework of equal opportunity, employment opportunity, and of a deep dedication to the fundamental tenets of human rights and dignity, And then skipping over here, in any conflict between technical expediency and human rights, we shall stand firmly on the side of human rights. So that's been a beacon to us for all of this time. They didn't just talk or write, they also put their ideas into action. And one of the first actions was to find a group of young men in Chicago who had demonstrated a technical aptitude to bring them to the laboratory and begin training them to be technicians, eventually engineers, and so on. Part of their training took place at the Oak Ridge National Laboratory in Tennessee, and here they are on the tarmac, I guess it must be at Midway Airport, about to board their flight to Oak Ridge for the beginning of their training. Many of these people have been with us for decades, and all of them are among the pillars of the laboratory. Wilson was a man who was born in a place that he called Frontier, Wyoming. No one knows whether it actually exists or not. And he wanted, again, this to be an American laboratory, so he imported 5 bison, to which the state of Illinois added a few other very early on. And as often happens when you try to do something interesting and good, it has unintended consequences. So the urban or maybe suburban legend grew up that the buffalo were actually here as canaries in a mine. There was no internet in those days, but had there been an internet, you would have read there that they're very sensitive to radiation, and when they detect radiation, their hair falls out. If you come back in the late spring, when they're shedding their winter coats, you'll find that all of their hair falls out. So don't be frightened by that, and come and enjoy our buffalo. So here was the groundbreaking for the main ring, our 2 pi kilometer around ring. You see everybody was there. Everybody's wearing hard hats except the boss. Everybody has a big clunky shovel instead of the boss. The boss has a gold-plated or maybe brass-plated shovel. If you'd like afterwards to come up and take a selfie with Wilson's shovel, please feel free, but don't harm anybody around you. And my chief operating officer will be happy if you wear a hard hat while doing that. So there it was. That was the beginning. I came here as a visitor. I was a fresh PhD, and I came here for a week in the spring of 1971, and I remember 2 things. One is that there was a lot of mud, and the second, that it seemed like a very exciting place. So now we look at the chain of accelerators. The first big piece of the accelerator was a reincarnation of one of the earliest accelerators. It's called a Cockcroft-Walton machine. This was the machine in England that was actually first used to artificially disintegrate the nucleus, and it still, until recently, served as the first stage of the accelerator at Fermilab. It's a very efficient way of getting up to a few tens of thousands of volts. Next comes the linear accelerator. And there it is. He's actually cleaning, not sleeping. It's called a linear accelerator because it's in a straight line. That's the second stage of the acceleration. Then comes the booster accelerator, which is just behind us out back, which takes the protons up to 8 billion electron volts. Here's some components of that being installed. You see lots of people doing lots of hard work in those days, and you saw some mud. Here's the main ring tunnel being finished. Again, lots of mud. This was done by cutting the ground away, so digging the ground away, installing a concrete flooring, and then using hoops to cover it, and covering that back up. And here's what the main ring looked inside. The reason for this plastic is that, as with many Bob Wilson constructions, the roof leaked, and so the magnets, which have plenty of problems on their own because they were really working to a tight budget and being exceptionally frugal, the magnets got wet and waterlogged and things like that. So the year before they got the machine to work, I was not a member of the Fermilab staff, but I'm told that it was the longest year in the life of many people who were doing that. But there was an end, and on February 12th, early in the morning, in 1972, they managed to accelerate the beam of protons up to just over 100 billion electron volts. The previous world record was held by a machine in Prodvino in the Soviet Union, which was 76 billion electron volts, and there was great celebration for having seized the world record. And in a nice touch, some of our colleagues from the Soviet Union contributed a bottle of vodka extra, which was drunk in the control room on the occasion of this. Now, on that very night, at 4 in the morning, the first experimental events were recorded. And this is a very interesting collaboration. This was in 1972. Richard Nixon and Leonid Brezhnev were the leaders of the two superpowers. They were both pretty tough characters. Nevertheless, they thought that it would be nice to encourage cooperation between the two superpowers, rival superpowers, in an area which could be of no threat to anybody, namely particle physics. So that was our good fortune. And through the friendships of some of our colleagues on this side and on the other side, one of the first collaborations formed was this one from the Soviet Union, the Joint Institute for Nuclear Research in Kuba, and from a number of American institutions, including Fermilab. They had a clever idea that, it was one thing to accelerate the protons to high energy. It would be another trick to actually get them out of the machine so you could do experiments. So they resorted to an old technique, which was intercepting the beam as it was circulating in the ring. And they did this with a thing that was a little motor that could turn at 3,600 revolutions per minute. On this was a polyethylene foil, specially shaped, so it went around and around like that. It would intercept the beam, and they could detect particles that were scattered by this very thin target, so thin that it wouldn't intercept, wouldn't bother too much, wouldn't absorb too many of the beam particles. And so they took their first data that very first night that the accelerator reached 100 GeV. I've now seen a photo of the prototype of their little apparatus, and I did a little research, discovered that the prototype was made in 1970. In 1971, someone else invented the weed whacker, and if they'd been a little faster to bring their invention to market, we could have paid for the rest of the experimental program. But they were focused on the physics. Later on, they added a new feature, which was to send a supersonic jet of hydrogen gas through the beam. That was even better, even more tenuous beam. And because they were inside the accelerator, they could actually make measurements as the beam energy increased during the acceleration process. So that was a very nice piece of work, and it was wonderful on the day the accelerator began to work to get some data. Within a couple of weeks, by the beginning of March, thanks to twiddling with some dials in the radio frequency building, the design energy of 200 GeV was reached, and that was cause for celebration, not with vodka, but with some unknown liquid this time. Oh, for the days of Dixie cups. Now, the first experiment to actually publish data came from this device called a bubble chamber. So this was a 30-inch in diameter device, under pressure, superheated liquid hydrogen, so that when charged particles fly through it and relieve the pressure, a chain of bubbles forms. They look like this. This was brought to us by people from Argonne National Laboratory, and I don't know if this is an early example of product placement or what in the right corner there. So the bubble chamber pictures are iconic and wonderful because they give you, when you take stereo views, three-dimensional views of the particles. It's a little clunky in the sense that it's slow, and you see a picture is there forever, but then you digitize the picture so it's real physics to analog to digital and back and forth. But they are beautiful and they're iconic. And we were all so taken by these when they first came because it was the first step into a new energy regime that we just wanted to collect these pictures. I remember Richard Feynman coming here and wanting to take home a sheet full of bubble chamber pictures because it was our first look at many particles, many was 10 in those days, being produced. Here's another one of those images. So they actually produced the first publication. Here's a standing table showing one of our scanners looking at the bubble chamber pictures. They would be projected on a very flat table, and then either using curved pieces of plastic or later on by being able to digitize them with electronic devices, one could measure the trajectories of particles coming out. So they submitted on the 21st of July, and this was published in the journal Physical Review Letters, the first experimental publication from Fermilab. What they did here was a stupendously simple thing. They simply counted the number of pictures they had, which there were 2 particles coming out, or 4 particles coming out, or 6 particles coming out. Some easy stuff. You've got to get the efficiencies right. Nevertheless, by looking at this, and then by some more complicated things, more sophisticated things that they and their competitors at Other Energies did in the succeeding months, we were able to learn lessons about how particles are produced out of the concentration of energy that comes about in these collisions that still hold today as our paradigm for the way particles are produced. And it was all because this is such a visual and revealing medium for doing experiments. That same summer, at the end of the summer, there was an international conference of high energy physics. This is our biggest meeting. It happens every 2 years. It was half in Chicago. There were parallel sessions at the University of Chicago where there are lots of rooms for small meetings. And then there were the plenary sessions in this auditorium, as you heard before, with the funeral directors' chairs taking the place of the comfortable seats that you have now. Our artist, Angela Gonzalez, designed the covers for the 4 volumes of proceedings of this. The first 2 speak to Chicago. The second 2 speak to what was to become the National Accelerator Laboratory. And this was for many people, especially from our colleagues from abroad, the first acquaintance they had with the new laboratory and the way it was working and getting started, and the first acquaintance with the Fermilab look, for which Angela was largely responsible. These many posters and covers of reports. It was, she did one for me. It was a very nice piece of work, I thought, and I had a cover from Angela. I thought I'd really done something. It's one of the high points of my own career. And the other aspect of the Fermilab work, which is a collaboration between Angela and Bob Wilson, is the bright colors, the strong forms that we have on the site. And the general look of the site. Again, you can see strong colors here and there in the high-rise building in which we find ourselves toward the background. Wilson also had a brilliant stroke. There's a cooling pond that you see, a canal inside the ring. That was needed to provide fresh water that would cool the magnets, the electromagnets that were steering the beam around. And he had the brilliant notion to use the dirt that was scooped up from there and put it on top of the beam, not as radiation protection, but so that if you were flying over, you could see the human beings had done something exceptional underground there. Instead of making it invisible, he wanted to make it visible. Before he hired me, he also gave me a test. He said that he learned that I came from California, not from some junior university, by the way. And so he figured I must like to ski, and he promised me that if I would come to Fermilab, he would take the dirt from the canal and build me the highest mountain in Illinois. So I'm pretty sure this was a test to see if I could estimate how high that highest building in Illinois would be, and I didn't want my name attached to it. Anyway, he did the right thing. Now, there is the matter of the high-rise. This lovely building, now called Wilson Hall. Wilson was a teller of tales, and so I can only report to you what he told me, not whether it's true. He had an artistic bent. And he said while he was contemplating what to make for the laboratory building, he considered various things, campus-style buildings relating to each other. But he was much taken with the French cathedrals that can be at great distance. He was reading, he says, Henry Adams' book, Mont Saint-Michel at Chartres, and that inspired him to make something here that could be seen from a great distance. So what you see back there in the mist is Mont Saint-Michel from a distance. As you approach it, it looms larger and larger and larger, and that was the model. So Here's our building with this great vault on the inside. There's another story also from French cathedrals that went with Wilson's story about this building, and that was that he was fascinated by the Cathedral of Saint-Pierre in Beauvais, about an hour and a half north of France. You see it on the left. You see it, great vault, on the right. So it has a little resemblance to our high-rise building, but not that much. But what really fascinated Wilson about this was that it was completed at the end of the 13th century. The people who built it, the local bishop and his supporters, wanted it to be the highest Gothic cathedral anywhere, and for 4 years it was, until it fell down. It was rebuilt after an interval of a century or so, and then a much higher tower was added to it, and after 12 years that collapsed. Wilson was a man who didn't like to over-design things. He liked to cut corners. Sometimes his things fell apart as well. So he was fascinated by the notion that you should do something impossible. And if it fell down, you'd learn your lesson and build it up. So that's the one thing he didn't visit to Beauvais is in this cathedral is installed in 1876. This is a very intricate mechanical computer that has 52 dials reporting various information, the phases of the moon, the position of the sun, the time of the day, the tides at Mont Saint-Michel, astronomical symbols and all of that, all done mechanically in the days before microprocessors. So if there happens to be an artistically inclined patron in the audience, I think we could use one of these to complete the analogy with that Wilson had in mind. I want to say a few words about my colleagues in theoretical physics. Here you see my colleagues in the theory group, plus a few of the people from nearby institutions and the rest of the laboratory who regularly spend time with us. They're all brilliant, as you've already heard. But what is a particular pleasure to me, and a particular pleasure of our everyday life, is that there are at least 15 passports, 15 national origins represented in this group of people. And that partly reflects the fact that this is a great lab that attracts the best of people from all over the world. Some of them have studied in the U.S., some of them have studied abroad. The people who come from elsewhere enrich our experience, and when they leave Fermilab, they are enriched by that. So that is part of my life that I value very much. What do we do? Well, what do theorists do? There's a lot of laughter, a lot of storytelling, there's a lot of coffee drinking. We make funny diagrams like this that we use to calculate things. We talk to our experimental colleagues, they bring us puzzles, we give them ideas that are sometimes brilliant and inspired and sometimes not. And the interplay between theory and experiment is one of the most satisfying things about our laboratory. Okay, now I want to turn to, we've seen a couple experimental results, but now I want to turn to Fermilab's first big discovery of the bottom core. Here is a proposal made by a small group of people, maybe 15 people, including Leon Lederman, who went on to become the director of the laboratory. I think this is basically the full technical content of their proposal, which is a far cry from the proposals that people make today in which they work things out. And I call your attention to point 2. Search for structures in the above spectrum, publish these, and become famous. Now, I don't know the basis on which this experiment was approved, but when I was serving on the program advisory committee, occasionally there was a proposal for which the only fitting punishment was to approve them and make them do it. This may be in that category. Well, do what they did. They built this wonderful spectrometer. So back here under the floor, a proton beam is coming up. It hits a target, goes through some stuff. And there are magnets that bend the particles that come out. And so you can add up their momentum and put them together. Here, I think this is the whole team when I add the two on the right that did this experiment. And they made a discovery. They found that when they added up the momenta of two muons, a mu plus and a mu minus, over a featureless background, there was this signal. It's like turning a radio dial. In some places you get a lot of interesting stuff, or noise or something like that. Elsewhere you get very little. If you look at this, you can see that there are at least two separate structures, and if you look very closely, you'd be induced to think that there might be three separate structures. This was enough, they followed up, of course, with more observations, to tell us that there was a new family of particles, as it happens, made by a new set of quarks, fundamental constituents that no one had ever seen before. Now, in the way that things go, this discovery, done with great labor in 1977, is now how our colleagues calibrate their apparatus when they turn on. So Fermilab is a big participant in the CMS experiment at